So what I've done is I've set up a coordinate system. Let me define positive directions. And I've taken out, from my previous picture, right, I've taken out the guy in the football, and I'm just drawing the trajectory of the particle. I don't need to call it a football or a baseball or whatever. This is just a particle. And it turns out that any object that's in these particular states, that is equilibrium in the x, free fall in the y, we can just consider to be a particle. And if I should formalize this, ay is equal to minus g. Of course, the minus doesn't have to be there, depends on your coordinate system. Ax is equal to 0. We call this the special case of projectile motion. Even if I have no motion in the x direction, I should point out, we still call that projectile motion. So you've actually already done some projectile motion problems. We did problems involving this acceleration in the y direction. We just didn't call them this, but now we're going to call them this. And the name is obvious. This is a projectile, right? If you fire a bullet or an arrow or something from a cannon, we usually call that a projectile. And this is the motion that it undergoes. Of course, the stipulation here is that we're ignoring air resistance. That gets us this nice equilibrium case in the x direction. But let's look at these situations. We've already figured out that v initial y is equal to v naught sine theta. V initial x is equal to v naught cosine theta. So I'm going to talk about the x direction. If there is no acceleration in the x direction, and we define acceleration as a change in velocity, notice this will never change. So v initial x is equal to v naught cosine theta, and that is also equal to v final x, and is also equal to every x velocity, every x component of the velocity at every point along the motion. If the acceleration is 0, it's not changing, and so it's v naught cosine theta everywhere in this motion. Now, the y direction definitely is not the case. The y direction is accelerated. Ay is equal to negative g, and so in the y direction, the velocity constantly changes. We've looked at that motion before. Remember, we talked about things go up, and they slow down, and then stop, and then turn around and speed up. So if we apply that thinking in the y direction here, maybe you can see that vy at the apex has got to equal 0. That's the point where it stops moving up. Now, is there a velocity is there a velocity at all at the apex? And yes, there is, because the x direction has not changed. In the x direction, remember, I'm still cruising along at a steady v naught cosine theta, so there is a velocity at the apex. There's just not a y component. It's all in the x direction. And then, of course, we have talked about the symmetry of the system. And if this is the case, if I'm coming down to the exact point, at least in the y direction, from which I left, then I know that my final velocity in the y direction is going to equal to the negative of the initial velocity. They're going to be going the same speed, just different directions. And so what I can say is that v final y is equal to minus v naught sine theta. Now, of course, if I don't have the symmetry, I can't do that. But at any point, this is one of the special points I can pick out, and just, if I know this, then I know this. Of course, there are other points in here. Let me pick out the one here. Looks like the velocity looks like that. Of course, I'm going to have a y component that looks like that. Probably should have done that in a different color. And an x component that looks like this. And so at every point in the motion, of course, I'm going to have different values of the y velocity. But I know how to find those because I've got the kinematic equations at my disposal. Now, what do I do with all these angles? Well, I know that I'm going to have to put them together at some point, because if I'm taking the motion apart and analyzing it in the x direction and the y direction separately, I'm probably going to have to put it back in at some point and figure out angles. And so I do that just like I've done all the other things. Let me get a different color. Or just like I've done all the other vectors, I use the Pythagorean theorem, right? if I've got v final x and I've got v final y, then it turns out that my v final, my whole vector, is equal to v final x squared plus v final y squared. And that's a square root. Of course, that's the magnitude. And then add an angle given by however you want to do it. Usually if we've taken these apart, we have analyzed it and determined v final y, determined v final x. So usually we use the inverse tangent v final y v over v final x. There are other ways to do that, of course, inverse sines, inverse cosines, but usually this is how we go because we've probably solved for the x and y components separately, and that enables me to get the final vector as the magnitude here and the angle given by this. Now, you got to be careful, as we've talked about with tangents. If you're talking about this vector and you plug in the negative v final y is negative, right? This will give you the correct angle below the x-axis. If you plug in positive values, it's going to give you the correct angle. And what I'm saying is if you plug in a negative value for one of these, it's going to give you a negative angle. That's fine because that works out just fine here. If you plug in positive values, it's going to give a positive angle, and then you need to recognize from your drawing that that angle is below the x-axis. Which way is correct? They're both correct. As long as you can keep up with what you're doing, it doesn't matter to me. My strategy is always to calculate this with positive values and look at my picture to figure out where my angle actually is. But you do as you wish.